July 1st, 2025. Astronomers in Chile detect a hyper-fast visitor from beyond our solar system, 3I/Atlas, on a path so precise it cuts through the planetary plane and threads just 18 million miles past Mars. This should be the moment every space agency springs into action. Instead, NASA's feeds go quiet, Mars orbiter teams erase scheduled updates, and professional skywatchers start whispering about engineered movements and mission-like odds less than 1 in 500. Why has the world's leading science institution gone silent as 3I/Atlas approaches Mars? Is this just an unprecedented interstellar encounter, or the start of something even stranger? The answers and the stakes begin here. Night falls over Teropachon, and the Atlas survey's automated telescopes sweep the southern sky, pixel by pixel. July 1st, 2025. A faint, fast-moving speck triggers a software alert, too quick for a typical comet, too bright to be a stray asteroid. Within minutes, the system flags the anomaly for review. On-duty astronomers, trained to separate cosmic noise from real discovery, pull up the flagged frames. The object's motion is unmistakable. A streak crossing the star field at a rate that hints at something extraordinary. The alert is logged, coordinates uploaded, and the Minor Planet Center receives a first report before sunrise. Confirmation requires more than a single night. The Atlas team, led by seasoned observers, scours their own archives and calls on colleagues at the Zwicky Transient Facility. ZTF's massive database holds every frame shot since early June. On June 14th, buried in the background of a routine survey, the same streak appears, fainter, farther, but following a consistent path. These pre-covery frames, once anonymous, now anchor the object's trajectory across weeks of sky. Each new data point sharpens the orbit, reducing uncertainty and ruling out known solar system objects. Rubin Observatory, not yet fully operational, offers a bonus: high-precision astrometry from June 21st, with position uncertainties so small they tighten the solution even further. The object is catalogued as C/2025 N1 Atlas, but its speed and direction raise immediate questions. Initial astrometric fits show a hyperbolic orbit, eccentricity greater than 1, and inbound velocity above 58 kilometers per second. The inclination, just under 5 degrees from the ecliptic, stands out against the usual swarm of comets and asteroids that cut steeper angles through the solar system. By noon, astronomers across the globe are checking their own data, confirming the discovery, and submitting additional observations. The Minor Planet Center posts an official circular, and the sky object is no longer just a curiosity. It's a global priority. Each archive, each time-stamped frame, becomes a thread in the story, stretching from the Chilean Andes to the data servers of California. The discovery, rooted in human vigilance and digital archives, sets the stage for everything that follows. Orbit modelers at the Minor Planet Center gather the first week's astrometry and begin running simulations. The numbers are stark. Inbound velocity between 58 and 61 kilometers per second, eccentricity above 1, and an inclination just under 5 degrees from the ecliptic. Most interstellar objects slice through the solar system at steep angles, but this one glides almost flat, threading the planetary plane like a probe on a calculated course. Statistical specialists feed these parameters into Monte Carlo ensembles, generating millions of synthetic interstellar entries using priors from Gaia and the Otautahi, Oxford ISO model. Out of thousands of simulated arrivals, only a handful skim the ecliptic by chance, and fewer still pass near any major planet. 3I/Atlas's projected path brings it just 18 million miles from Mars, a proximity unmatched by either Borisov or Oumuamua, both of which passed far outside planetary spheres of influence. For analysts, the geometry stands out. A corridor so flat and precise that some begin calling it mission-like in private Slack threads and technical notes. The odds of such a coplanar, multi-planet sequence are difficult to pin down. No published study offers a definitive figure, but dynamicists agree that the configuration is rare. NASA's own orbital dynamics group, referencing the simulation outputs, describes the path as statistically remarkable, an event not predicted by standard models of interstellar traffic. The lack of a peer-reviewed probability keeps speculation in check, yet the numbers themselves invite debate. Comparisons with 2I/Borisov highlight the anomaly. Borisov's closest planetary approach was over 150 million miles, and its inclination cut steeply across the ecliptic. 3I/Atlas, by contrast, arrives almost as if targeting the planetary plane. The simulation teams, seasoned by years of tracking comets and asteroids, find themselves recalibrating expectations. Each new data point confirms that the object is not bound to the Sun and will never return. The question lingers: how does an interstellar traveler thread such a narrow path, and what, if anything, does it reveal about the forces that sent it here? No press bulletins, no mission updates, no raw data streams. As 3I/Atlas swept toward its closest approach to Mars, the usual rhythm of public communication faltered. Agency websites, once lively with comet news, slipped into routine posts about instrument health and calibration. Mars Express and Trace Gas Orbiter, both positioned for a front-row view, published only generic science logs. No mention of the comet, no special bulletins, no images outside the standard archive cadence. Amateur astronomers, who had filled forums and Discord channels with nightly tracking reports, found themselves starved for new data. The drop in updates was abrupt. Cloudy Nights threads slowed to a trickle. Telegram groups, once abuzz with predictions and live photometry, turned to speculation and recycled ephemerides. Even the most committed observers could only point to gaps. No fresh images, no official word, no answers. Technical logs and back-end feeds told a different story. Telescope schedules showed last-minute retargetings, with Mars orbiters quietly slipping in new coordinates and spectrometer settings for volatile and organic signatures. Yet none of this activity surfaced in public-facing channels. Instead, the silence spread. Routine Mars weather updates, calibration notices, and planetary science news filled the void. But the comet's passage, so close, so rare, was left unmentioned. For those watching the feeds, the expectation was clear: a cascade of images, spectra, and analysis as the interstellar visitor brushed past Mars. Instead, the silence held. Each absent update, each missing data drop, left a growing question. Was this just operational caution, or a deliberate decision to keep the world in the dark? The gap between what was possible and what was shared became impossible to ignore. At 6.4 astronomical units from the Sun, well beyond the frost line where most comets remain dormant, 3I/Atlas erupted in brightness. Southern Hemisphere photometry teams logged the first spike, a sudden surge in light, then a fall, then another rise, each burst lasting hours to days. The pattern didn't match the slow, steady outgassing seen in classical comets. Instead, the light curve pulsed with a rhythm, as if the object itself were breathing. Observatories from Chile to South Africa scrambled to confirm the signal, and each set of data returned the same result: activity where none should exist, at a distance where solar warmth cannot drive water ice to vapor. Dust analysts poring over high-resolution images found the next surprise. The tail, expected to stream away from the Sun under radiation pressure, bent back toward it in segmented arcs. Models predicted a simple, sun-fleeing plume of fine dust. What they found instead was a tail dominated by heavy, slow-moving grains, particles that should have settled out or barely escaped the nucleus's gravity. Spectral analysis revealed an unusual dust-to-gas ratio, with the coma's mass far exceeding what a nucleus under 6 kilometers across could supply. Some calculations demanded a core up to 10 kilometers in diameter, yet direct imaging from the Hubble and Rubin observatories held the upper bound firm at less than 6. Each anomaly deepened the puzzle: the rhythmic outbursts, the sunward tail, the mass mismatch. Every finding forced a new round of calculations and late-night calls between teams. For physical scientists, the comet's behavior was not just rare, but inexplicable under known physics. The object that had started as a curiosity now demanded every available instrument, every hour of observation, and every ounce of scientific creativity. Inside control rooms from Madrid to Pasadena, the pace accelerates. Mars Express planners upload a new sequence. HRSC and Omega, tuned for volatile organics, are given priority over routine atmospheric surveys. ExoMars Trace Gas Orbiter's Nomad spectrometer receives an urgent override, its settings shifted to low signal mode for faint, fast-moving targets. Each deviation is logged, each request flagged as a target of opportunity. Routine Mars weather campaigns are deferred. Comet tracking takes precedence, but only for a handful of days. On the ground, Chilean and South African observatories scramble for clear skies. Schedules bend to accommodate late-night comet passes, with teams running photometry through dawn. In Australia, radio telescopes join the campaign, searching for any trace of non-thermal emission. The James Webb Space Telescope, after weeks of negotiation, carves out a high-cadence emergency slot, just hours before the blackout window closes. Hubble, facing the same deadline, pivots to rapid-fire imaging, squeezing in one final sweep before solar conjunction. Coordination runs through encrypted Slack channels and phone calls. Engineers at ESA's Deep Space Network reallocate downlink slots, pushing Mars Express and TGO data ahead of scheduled calibration dumps. Instrument teams argue for longer exposures, risking thermal constraints and data gaps elsewhere. Every adjustment is documented, every minute counted. The sense of urgency is palpable. This is the last clear window before the comet slips behind the sun, taking its secrets with it. For a brief, fevered stretch, science races the clock, and every photon counts. October 29, 2025. The sky map for 3I/Atlas dissolves into static as solar conjunction draws a hard line across the observing world. Hubble and the James Webb Space Telescope, both bound by strict solar avoidance angles, enter their scheduled safing blocks. Ground-based telescopes from Chile to Hawaii log their last frames and turn to other targets, their operators resigned to a 10-day blind spot. For the first time since discovery, the comet is unwatchable from Earth, a natural blackout enforced by orbital mechanics. Inside mission offices, the atmosphere grows tense. Internal memos circulate with subject lines stamped Operational Security Blackout. Mars Express and Trace Gas Orbiter, having just completed a fevered week of comet tracking, switch their public feeds to generic logs. Instrument teams are ordered to embargo all high-resolution data and suspend external communications until further notice. Slack channels fill with frustration as junior analysts question the clampdown, while senior staff cite the OS-3 protocol. No raw data, no spectra, no time-stamped orientation files until the blackout lifts. Solar observatories, SOHO and Stereo, remain the only sanctioned eyes on 3I/Atlas. But their vantage is limited, and their data streams are filtered through the same security review. Mars-based assets are now silent, their unique window closed by geometry and directive. The world waits in enforced ignorance, the fate of the interstellar visitor hidden behind both the sun and a wall of embargoed files. By November 10th, the blackout will end, but for now, the story of 3D/Atlas hangs in the balance, unresolved, unconfirmed, and out of reach. October 31st arrives with 3I/Atlas hidden behind the sun, unreachable by every telescope on Earth. In control rooms, modelers run final simulations, each scenario branching into uncertainty. Direct imaging from Hubble and the James Webb Space Telescope, gathered before the blackout, sets the nucleus diameter below 6 kilometers, but coma mass and dust production hint at something closer to 10. The numbers refuse to settle. Some teams argue for a hollowed core, others for a volatile-rich interior capable of explosive outbursts. The fate of 3I/Atlas rests on three possibilities: catastrophic fragmentation, an eruption that leaves only debris, or survival, intact and unchanged, through perihelion's heat. None can be confirmed. The last spectra from Mars Express and the Trace Gas Orbiter, embargoed and incomplete, offer no closure. As the world waits, every analysis is provisional, every model contested. The comet's closest approach to the Sun plays out in silence, its true nature and outcome sealed behind geometry and embargo. For now, the story holds at its apex, all answers out of reach. Calls for openness echo across scientific forums and public platforms as the blackout lifts and the world confronts what it still does not know. Policy advocates, once sidelined, press for real-time data sharing in future interstellar encounters. The absence of transparent updates during 3.1/Atlas's closest approach to Mars has become a rallying point, not only for planetary scientists, but for a wider community demanding accountability. Drafts circulate for rapid response mission proposals, dedicated interceptors, probe launches, and standing observation networks, designed to ensure that the next interstellar visitor is met with more than repurposed instruments and embargoed logs. Open-source researchers publish their analysis code and data notebooks, inviting peer review and public scrutiny. In virtual town halls, astronomers and citizen scientists debate the lessons of this encounter, pointing to the gaps that secrecy left unfilled. The unresolved mysteries of 3.1/Atlas, its origins, its composition, the true nature of its passage, now serve as both scientific challenge and civic imperative. For many, the call is clear. The next time the cosmos sends a message, humanity must be ready to listen together. On October 31st, 2025, 3.1/Atlas passed behind the Sun, leaving Earth-based observatories in a complete blackout. Archival logs confirm its hyperbolic trajectory, with a velocity near 61 kilometers per second and an approach just 18 million miles from Mars, unlike any previous interstellar object. Despite coordinated campaigns and emergency retargeting of Mars orbiters and space telescopes, critical data streams fell silent. Internal documents marked operational security highlight the unprecedented secrecy surrounding the event. The scientific record shows rhythmic outbursts, sunward tail bends, and a persistent mass discrepancy, none explained by standard comet models. Yet the true size and structure of 3.1/Atlas remain unresolved, and the reasoning behind institutional silence is still classified. Today, the case of 3.1/Atlas stands as both a milestone in interstellar science and a reminder. Even with global resources, transparency, and rapid response remain unfinished challenges when faced with the unknown.